Today, we're going to be talking about dosaging of medications and how that relates to half-life. Half-life is the time it takes for half a substance to remain. So you've heard about that before in something like carbon-14 dating with old fossils and things like that. Carbon-14 has a really long half-life. It takes thousands of years for half of it to remain. We're going to be working with medications, and that works more on the line of hours. So our half-life formula here is A sub T sub half, so the half time amount, equals A sub 0, or your starting amount, times e to the negative k times t power, where k right here, that's what we call the constant of elimination. That's the same thing as the constant of variation that we learned about back in Algebra 2, but since we're applying it to half-life formula of medicines, it's a constant of elimination because we're eliminating it from the body. So, what we need to do here is we need to take some known information and solve for that value k. So we're going to go ahead and start out with caffeine today. Did you know that it takes a healthy adult about 3 to 4 hours for caffeine to have its half-life? About 3 to 4 hours it remains. For a pregnant woman, it's about 9 to 11 hours. And young children, you ever seen a young child drink a soda and go bouncing off the walls all night? Well, for a young child, it's actually 20 to 30 hours. So think about it, about 25, 24 hours, a full day, and they've still got half the soda in there. And people with liver disease, up to 96 hours. That's 4 days before half of the caffeine has been eliminated. So let's go ahead and stick with a healthy adult, and since that was 3 to 4 hours, let's go with an average of about 3.5 hours. So what we're going to do is we're going to say, let's say we take 1 tablet of caffeine, or we drink a soda, right? And that's about 50 milligrams of caffeine. So half of that would be 25 milligrams. So we're going to go ahead and our starting amount is 50. Then we've got this, and we're going to multiply that by E times negative K, that's what we're trying to figure out, times T. How long did we say the half-life was for caffeine? Well, we said it was about 3.5 hours. So we're going to put 3.5 right there. Now, before we go too much further, I want you to notice, do you recognize this formula? Now that we've put some numbers in it, does this look similar to you, to anything we've worked with before? Yeah. How about our good old friend APERT? Continuous compounding. A equals principal times E to the rate times power. It's the same basic formula, and it's the continuous compounding formula because elimination of a medication from the body is happening continuously. So, let's go ahead and move on. We're going to go ahead and divide out the 50 here so we can get K by itself. Divide out the 50. And so 25 divided by 50, notice, is a half. That's not a half, Mr. Manning. That's a fifth. There we go. There's a half. And the 50s cancel. Equals E. And let's go ahead and put this as negative 3.5 K. Write it in the more standard form. Now, how are we going to bring that K down so that we can go ahead and solve for it? Anybody remember that next part? Yes. Natural log both sides. So if we natural log E, that eliminates leaving just this side by itself. So we now have the natural log of 1/2 equals negative 3.5 times K. You got it. All we have to do is divide out that negative 3.5, and we are ready to solve for K. So there is our value for K. So what is it? K is approximately 0.1980 blah 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 blah, so 0.198 we'll say. So that's the value we need to know. Now, before we go on too much further, I want you to recognize what's happened here. We're talking about half-life. So we're always going to be taking half of the substance over here, right? So that means when we divide, we're always going to get the number 1/2. right there. So where did 3.5 come from? Right, that was time. So what we can realize right now is that our constant of elimination formula can be rewritten as the natural log of 1/2 divided by negative time. And that's a generic equation for the constant of elimination. Up here, there's our equation for the half-life formula. So let's go ahead and try some examples here with caffeine. So let's take this value here. K is approximately 0.198. We're going to take that with us. K is approximately 0.198. And what we're going to do now is, if the starting amount is 100 milligrams, that's like an espresso, I understand, and T is 5 hours, we want to know how much is left after 5 hours. So find A sub 5. Okay? So what do? Well, we substitute what we know. We don't know the end amount, A sub T. That's A sub 5 is what we're looking for, so we can go ahead and rewrite instead of a T. We can go ahead and put a 5 there. And A sub 0, our starting amount, we do know is 100, times E to the negative K, 0.198, times time, 5 hours. Now, this we can put straight into our calculator pretty much, and our calculator would look like this. 100 E, we don't have to put multiplication because it's implied multiplication. E will start a caret and a parenthesis for you, and you're going to put in negative 0.198, multiply 5, and close that parenthesis. And what we're going to find is that A sub 5 is approximately 37.15. So let's call that 37.2 milligrams. Okay, so after 5 hours in a healthy adult, after drinking, say, an espresso, about 100 milligrams, that's going to be about 37.2 milligrams still remaining. Okay, so now let's try a different question. What if we know after 5 hours, A sub 5, the amount after 5 hours equals 37 milligrams. And we want to know, we drank the drink 2 hours ago. Sorry, 5 hours ago. 5, right? We put a 5 there. What we want to find now is how much did we start with? What was the original amount? So, again, substitute what we know. This time we know the ending amount, 37. We don't know the original amount, A sub 0, times E to the negative 0.198. Remember, that's the constant of variation that we found for a healthy adult drinking caffeine. That would change if it was not a healthy adult, if it was one of our other types of people, or it could possibly change if it was an entirely different medication. So finally here, we've got 5 hours. We're going to put the 5 right there. And so how are we going to solve this? Well, what we're looking for is this value. All of this is what's connected to it by multiplication right there. So let's divide that out. So let's divide both sides by e to the negative 0.198 times 5 power. Divide e negative 0.198 times 5. Now again, that cancels, and we get this for our answer. Well, again, that goes into our calculator at this point. So it would look like 37 divided by e starts a caret and a parenthesis, and you put in negative 0.198 times 5. Throw all that in the calculator, and we end up with the original amount is approximately 99.57 ... So that's approximately 100 milligrams, right? If we round to the nearest whole number, 100 milligrams. So you notice we're doing the same problem from 3 different directions. Finally, if our starting amount is 100 and our amount after some amount of time is 37 milligrams, find the amount of time, find T. So again, we substitute what we know. Final amount's 37. We start with 100 times e to the negative 0.198 times t power. So this time we have our variable as a power. So we've got to use the definition of a logarithm eventually. First, we have to divide out this 100. Now 37 over 100, we could write that as a nice clean decimal, 0.37. Or you could leave it as 37 over 100, either way. So that's going to equal negative 0.198 times t, e to that power. And how are we going to get that to come down from e? You guys remember it, don't you? Natural log both sides. So that cancels, and we end up with the natural log of 0.37 equals negative 0.198 times t. Divide that out, right? And we end up with, the natural log of 0.37 divided by negative 0.198 equals t. And again, plug that in our calculator, and t comes out to be approximately 5.02, or approximately 5 hours. So, there are 3 examples of the 3 different potential problems we could solve with this. I hope this helps out. In the next one, we're going to talk about redosing, what happens when you add to this amount. I'll see you then. Bye.